Let me start by thanking the organizers for putting together this very nice workshop and allowing me to speak here. It's a great pleasure for me to give this second lecture of the day, especially because this research topic aligns more or less exactly with what I'm working on myself, which is really the intersection of all these ideas of tameness, o-minimality, and applied physics. This is going to be the lecture where we kind of continue from what was presented in the morning about o-minimality and also how to make this more quantitative with complexity and applying these ideas to physics. So let me reiterate that we have a very diverse audience of both mathematicians and physicists, and I'm going to try to present a story that is very comprehensible for both sides of the audience. Nonetheless, if you have any questions, please do feel free to interrupt. It's going to be my intention that this is quite informal. So let me start with some motivation for this topic. I want to start by raising a question, namely, what is the language of physics? It's a very philosophical question, and I think it admits a rather straightforward answer, namely mathematics. It's fair to say that in our descriptions of physical theories, we more or less always use some kind of mathematics. But of course, I want to go a little bit beyond that and ask, well, what kind of mathematics? So the heuristic picture is that there is a very big space of different mathematical theories. This is by no means a well-defined space, but trying to classify different mathematical theories according to their logical properties is a discipline within mathematics known as model theory. So what this field does is try to understand different kinds of theories in mathematics. What kind of logical properties do they satisfy, like decidability, completeness, and so on. And this is actually also the field where tameness in the form of o-minimality originates from. So within this kind of abstract space of mathematical theories, there is a particularly nice subregion of theories which satisfy this o-minimality axiom. Okay. Now this question of what is the language of physics also depends on what kind of physics we consider. Right? There's not just one theory of physics, there are many different frameworks, theories. So in parallel, we actually have a gigantic space of physical theories. And this is also by no means a well-defined space, but if you want to be a little bit more concrete, you can think of this as, for instance, the space of all possible quantum field theories, just to make it slightly more concrete. Okay. Now there's a relation between these two spaces, basically determined by whether a given physical theory has a certain realization as a mathematical theory, informally speaking. So you can say you have a physical theory, and you can describe that theory with a certain mathematical language, which would correspond to a point in this space. Now, this lecture is going to be about understanding this connection between these two spaces. So, in particular, what kind of theories land in this o-minimal region? So, which theories can you describe with o-minimality, and how is this o-minimality realized in physical theories? And here we will soon realize that, well, not any physical theory can be described within this language of finiteness. And a rather amazing selection principle emerges here. Because you can ask, well, ultimately you have a big space of physical theories, but which ones describe the universe that we live in? This is ultimately the goal of physics. And well, our universe is more or less unique, right? So we expect there to be ultimately one single theory which describes our universe, which may be, for instance, realized by quantum gravity. And you can now ask, which theories in the space of physical theories can be consistent with such a theory of our universe? Okay. So for instance, if you want to approximate something at low energies, which descriptions are valid as a description of our own universe. And it turns out that this consistency with our universe, by which I mean more precisely that it is consistent with quantum gravity, which is what David will explain a bit more about, you find that this is actually an extremely constrained region in the space of physical theories. Okay? And it was realized roughly 20 years ago that these constraints are all kind of based on various facets of finiteness. And this is what is known as the swampland program, initiated by Rafa 20 years ago. And the idea is that most of the theories in the space of physical theories, more precisely the low energy effective field theories, are actually not consistent with quantum gravity, and they form a sort of swampland. And the theories which are then somehow constrained by all sorts of finiteness criteria. And the aim of this program, the swampland program, is to kind of make this boundary precise and understand which theories are consistent with quantum gravity.
Sorry.
Yes.
What is a physical theory?
Here I mean very loosely, informally, a kind of thing that's something a physicist studies, basically. So there's no formal definition of physical theory. It can be a model which is physics inspired. It can be a framework of theories like quantum field theory, but it's supposed to be a heuristic picture. So there's no well-defined.
But do they study like different universes, or what's the? I mean, why should we? What's the goal?
Well, you can set up this framework of quantum field theories, right? And you can say, well, these are physical theories because they're inspired by physics, but they turn out not to all describe phenomena in our universe. Or maybe some restricted class of phenomena, but I'm really thinking globally about theories of physics. Okay, well, roughly 4 years ago, it was realized that these theories which fit in this region of physical theories can be very nicely described with tame geometry. This was a realization by Thomas roughly 4 years ago. But the picture that emerges is that the theories in this space actually seem to be landing precisely in this part of the space of mathematical theories. And this is formalized by what is called the Tameness conjecture. So the global picture of this lecture is going to be, if you constrain to physical theories consistent with quantum gravity or our universe, then they seem to all land in a particular class of mathematical theories, namely those which satisfy the o-minimality axiom. And this is going to be the topic of this lecture. Let me quickly, to extend the motivation, explain a few reasons why this might be interesting. First of all, I think it's for intrinsic reasons interesting to try to narrow down what kind of mathematics is ultimately consistent with quantum gravity. So in that sense, it may give new perspectives on quantum gravity and what kind of mathematics you need to describe it. More pragmatically, you can also think of the very nice theorems which are valid in o-minimal structures, some of which were mentioned in the lecture this morning, like these point counting theorems, cell decomposition. And if this picture is true, then you can apply all these theorems very globally to this set of physical theories. Okay. And also more on the pragmatic side, you can then try to use sharp o-minimality to assign complexity or a notion of information into physical theories. This is going to be the motivation for this lecture. And now I start with the first part, which is about Tameness in quantum field theory. So my part of the lecture will focus more generally on how o-minimality is realized in physical theories, in particular in quantum field theories. And David will focus more on narrowing down this perspective to theories consistent with quantum gravity. Are there any questions at this point?
When we say that physical theories mean that the observables are of this nature, and we have like intermediate steps that are very transcendental and conspire to then be name at the end, or it's the
Exactly. So you can take two perspectives. You can start with the description of the theory itself. Can you give somehow some tame data which describes the theory? Or do you look at what happens after you sort of do the calculations and the outcome, so more the observables? We will take both perspectives in this talk. Yes?
Is that upward arrow real?
Sorry?
Is the upward arrow in your diagram, does it exist?
No, it's more to indicate that it's not a map from one space to the other. It's rather a relation.
Oh.
So I didn't want to specify it as just an arrow indicating a map. Because, well, a different physical theory can have different mathematical realizations, depending on your description. So that's why there's not really a map from physical theories to mathematical theories, rather some kind of relation that can go in both directions. Okay, well, to start this section, I want to dedicate a few words to what a quantum field theory is. Because I'm not assuming that everybody is familiar with quantum field theory. So it's not my goal to review all what quantum field theory is about, rather to give a quick working definition and introduce some of the concepts that we're going to use in this talk. So basically, in words, quantum field theory is a framework of physical theories with the goal of describing the interactions between elementary particles, so very small processes, by the laws of quantum mechanics. But for this lecture, what is important is what kind of objects appear in this theory. And the most simple starting point is to basically specify, first of all, two manifolds. First of all, a manifold X, which is called space-time. This is just a manifold through which we envision that the particles move. And in addition, we have another manifold we're simply going to call field space, which is roughly where the fields in quantum field theory will live. And then a field is basically nothing but a map from space-time into this field space, okay? At least classically for the physicists. And these fields are somehow going to describe interactions between particles. What I further need to specify is some real-valued function of these fields, as well as some parameters. And this function is called the Lagrangian. If I specify this function, I basically specify how the fields are going to interact on space-time. And for the physicists, of course, not all quantum field theories have such a description, but throughout this lecture, we will consider theories which have such a description.
If you have fields of many different types, why is it that there's only one manifold, which is your field space? Like, why don't you need one for boson, one for something else? Why is it that there's just one manifold that?
Yeah, so in that regard, I would take this space M to be the union of all these, or the product of all these spaces.
Okay.
Yeah, so this factorizes into spaces corresponding to different types of fields. But in this lecture, we mostly focus on scalar fields. Well, the main point of this statement is that basically we have a bunch of real geometric objects, and it now becomes already a well-defined question to ask, well, in what cases are these tame or definable objects? Once I've specified this data, the main objective of quantum field theory is, as I said, to describe these interactions between particles. And these are described by a set of real-valued functions called amplitudes. And these are functions of some real variables p, which collectively describe sort of the information of the physical process, as well as these parameters which appear in the Lagrangian. Okay, for us, it doesn't matter really how you calculate these things, but the calculation of these objects, these real-valued functions, is really somehow at the heart of quantum field theory. And indeed, you can now ask, well, what kind of functions do you get from quantum field theory? And are they definable in any o-minimal structure? That's the main point I want to convey with this little quantum field theory review. Any questions at this point?
How are those amplitudes related to this data? That's it.
Right, so essentially, this is where the real framework of quantum field theory comes in. Basically, it's defined through something called the path integral. Yeah, it's not my intention to really explain in detail how this works, but it's a complicated calculation. And I'm going to, in the course of the talk, explain a little bit more how you should do this. And indeed, it's typically too complicated to really fully calculate these functions. So instead, you take a sort of simpler approach called perturbation theory. The next part of the section. Perturbative amplitudes. Basically, the idea is that this function as a whole is extremely hard to calculate. So you split it into simpler pieces. Namely, you perform a power series expansion. Basically, you extract dependence on the parameters appearing in the Lagrangian in the form of a power series. And then these individual pieces will be called the perturbative amplitudes. And for these, there is a rather simple, though tedious, algorithm to compute this by means of these Feynman diagram pictures that you may have seen if you're not a physicist, and definitely if you are a physicist. And these pieces are basically more tractable. So I want to start by looking at these pieces. And now there's the first theorem that I quickly want to state, which is due to Mike Douglas, Thomas Grimm, and Lorenz Schlechter, which basically says that if you take this Lagrangian, which specifies how the fields will interact, to be a polynomial, and for the physicists, you also ask that the theories were normalizable. Each of these perturbative amplitudes appearing in this power series expansion is definable in the o-minimal structure R on X. So this extremely general class of functions, depending on this data, if you calculate these amplitudes and carry out this procedure, what you find is that all these functions are always definable in an o-minimal structure. So they're always tame. And it's quite remarkable because, well, you see there's not too much dependence on the input data.
Sorry,
So this is an
explain what P was.
P, sorry, what?
The arguments you're.
Yeah, but these are basically the kinematic data of the physical process that you try to describe. So let's say you have a bunch of particles, they may have some momenta, energies. Those are the P's. And the lambdas are variables which parameterize the theory.
But these P's, are they fixed as part of your quantum field theory, like data that you fixed at the beginning?
No, these are not part of the data. These are part of the physical process that you describe. So for each physical process, there is a different amplitude function. So it's a collection of functions.
So you somehow you ask a question of the theory, and then depending on that question.
Precisely, yes. So
Even more basic, but when you say definable normal, is it a map from two spaces and they come with a definable structure and then it's defined? I mean, what? I mean, A, K, P, so it's a map from what to what?
so I mean, as a function of P.
Yeah.
Yeah, this is a map from P, it's a real variable.
So where does P live? It's just in Rn or some manifold?
Ah, yeah, okay, good point. Yeah, so P is basically in some Rn. It consists of the momenta.
A is a map from Rn to what? What's the output? It's again.
It's a probability density, so it lands in 0 to 1, basically. Yeah, it's a real valued function in particular.
Complex, huh?
Sorry?
Amplitudes can be complex.
Yeah, but I'm talking about the amplitude squared.
All right.
So you said this is a perturbative approach and lambdas are the parameters. So I suppose
Yeah.
that lambda equals to 0 is some simple thing that you're perturbing. So what are you perturbing?
Ah, yeah. I'm basically perturbing around a sort of trivial theory for which the amplitudes are kind of trivially calculated, and I'm adding a deformation corresponding to some kind of complicated interaction between particles. It's a very good point. Yeah, so I'm starting around a sort of trivial point where everything is known, and then perturbing into something which is more complicated. And I'll give a concrete example of that later.
So in this, theorem, so you have L is polynomial, but you're assuming something about L p comma 0. Like, you said that if L is polynomial, you have something, but it seems like there should be some assumption about L of p comma 0, right? In the theorem. Otherwise, how do you?
Ah, yeah. So this also assumes that we are expanding around that free theory.
Yeah. So so this okay. So L of p comma 0 is not some free or something.
Yeah. So basically, let me write this down. So lambda is some lambda 0.
It's always of this.
It's always of this form. That's exactly. Yeah. And for this theory, the amplitudes are sort of trivial to calculate because there are no.
You said it's polynomial. You mean the dependence on lambda is polynomial, or in L0 and L int they are like polynomial depending on phi?
The full Lagrangian. So this object is polynomial. Yeah. Yeah. Exactly. Yeah. Very good questions. Thank you.
You said you were working on manifold X, but now, so P is, now X is flat space.
Exactly. Yeah. Yeah. I'm stating it somewhat informally, but there are further assumptions. X is now a flat space. Yes. Any further questions about this statement? If not, my intention is not to prove this, but let me quickly sketch the idea. And if you're familiar with this o-minimal structure, this might already raise some suspicion where this theorem comes from. Namely, the idea is to use the tameness of the period map in Hodge theory. That's proven by Bakker, Klingler, and Zimmermann a few years ago. And also an extension by Bakker and Roulin a few years after. So I guess we'll see much more of this in the lecture about Hodge theory. But basically, the period map is definable in this o-minimal structure. And the idea behind the proof is to map this algorithmic approach of calculating these perturbative amplitudes to periods, and then translating those into basically tame functions. And then, because you only have finitely many processes at each order of perturbation theory, you will find that the whole function is tame.
But are you thinking the X, M, and your field phi, they all come with some sort of definable structure, or they can?
Yeah. So in this theorem, it's just some Euclidean space. And in particular, so is this field space.
What about the map, the field?
So this field is not part of the defining data. This was just to indicate that the fields are maps between these spaces. But these are the variables in the theory, so to speak, the degrees of freedom. Yeah. Okay, so this is basically covering the perturbative amplitudes. But can we also go beyond this and make any statement about this full amplitude? That's going to be a non-trivial step because basically I'm adding infinitely many discrete pieces of which I know that they are definable, but there's some much harder to control. But nonetheless, there are a few statements that you can make in very restricted settings. And I want to highlight a few of those now. So 2.3, What about non-perturbative amplitudes? Well, and first of all, there is already the problem of that this is much harder to calculate. Even much more fundamentally, there's the problem that this series actually doesn't even diverge typically. Okay, so we can say a lot about these individual pieces, but the whole thing, this is not a convergent expression for the full amplitude. So we need different tools to actually say anything about the tameness of this full object. The series diverges, and in particular, it's some kind of asymptotic expansion. So basically, we can only say something for now about the tameness of these full amplitudes in extremely special settings where we have more control. And these could include something like very low dimensions or theories with a certain degree of supersymmetry. And I'm going to give one example of the former with very low dimension. So let's go to the lowest number of dimensions, namely 0 dimensions. So we take the space-time manifold X to be simply a point, and we take the field space to be the real line. This is hardly even a real quantum field theory anymore because there are no moving particles, but it retains some of the essential features of this theoretical framework. And what we can do here is, because the theory is so much simplified, we can do exact calculations, and we can basically skip this intermediate step and go directly to the full physical amplitude. Basically, the amplitude takes the following form, where now n is some kind of discrete label, labeling the physical process. Simply an integral over phi, and then the exponential of minus the Lagrange. Okay? So for the physicist, this is just the Euclidean path integral on a point. It takes this form of an ordinary integral.
He runs over some compact interval, or
No. So I take
P runs
n
over
to be the
R?
real line. So it runs over the whole real line. Yes.
L, you are taking polynomial. What is your assumption about the Lagrangian?
For now, nothing, but soon I will specialize the polynomial. Yes.
Sorry, that series always diverges, right? Even in normal QFT, even
Yeah,
in perturbative,
always,
right?
always.
So when
Yeah.
it's non-perturbative, you're trying to say something extra happens, right?
Exactly.
So what's so it always diverges. So what's the extra step in the non-perturbative case?
So basically, this kind of expression would be the true quantum field theory expression for the amplitude. When we do the perturbative expansion, we're basically taking this L as this deformation and kind of integrating this thing one by one, order by order. And because of this step of changing the order of integration and summation, that's why the series diverges. But here we can actually just simply forget about this and directly calculate the integral if L is sufficiently simple. So just to give you a quick example, which we discussed in a paper with Thomas, Lorenz Schlechter, and myself. Let's say you take the simplest possible interaction. So you take a Lagrangian to be 1/2 pi squared. This is this kind of trivial piece that I mentioned. And then we take a deformation corresponding to a general polynomial of phi. Okay. Now, if we take this polynomial to be quartic, so phi to the 4, what we show is that this amplitude is actually a Pfaffian function. on the open interval from 0 to infinity. Okay, so these Pfaffian functions, which were discussed in the morning, we basically find these in these amplitudes, in the non-perturbative amplitudes. But notice that the range of lambda doesn't include 0. That's exactly because of this non-analyticity that you already mentioned. Just to give you an example of what these functions look like, if you take n equal to 0, so just e to the minus this Lagrangian, you calculate it, you find the following function. And this is the modified Bessel function, the second kind. So what was already mentioned in the lecture this morning, that sometimes you can make statements about Bessel functions. Here we explicitly find a Bessel function in the simplest possible non-perturbative physics amplitudes. Okay. As I mentioned, there's a big problem with taking lambda to 0, basically that this series is not analytic. Okay. And of course, Pfaffian functions are analytic. So if you want to make any tameness statements beyond this class of functions, we will need basically a more general class of functions, which are still o-minimal. This takes us to the second part of non-perturbative amplitudes.
So just to clarify, your A superscript n lambda is your analog of AKP. This A superscript with an n lambda, is that supposed to be the analog of AKP on the other side?
No, it's supposed to be the full.
It's supposed to be, okay.
Yeah.
So what would be the coefficients? Is it easy to explain the coefficients are?
Is n?
So no, so if I wanted to understand the AKP, so where you write that big summation.
Yeah.
And you extract the coefficients of lambda.
Yeah.
Is it clear what they are in this case?
No, this would be the full sum, including all orders of k.
But wouldn't the
He's
coefficients
asking-
be 0?
I think he's asking what happens when you write an asymptotic series for.
Yeah, so what would, I mean, is it easy to write out the asymptotic series for this expression?
Ah, sorry, yeah, now I understand. Yes, exactly. So because the theory is so simple, you can also write down the asymptotic series. And you find that the coefficients in the series grow factorially. So you explicitly see that.
Because I'm trying to understand the connection with this theorem where it says that this is a kind of definable function.
Yes.
And so in this case, it was some function from like, I guess, Rn to R or something.
Yes,
But here you seem to be indexing by a discrete parameter.
exactly.
Like
Yeah.
E being a real value thing. Is that right?
So this n is an integer, and it basically is a label corresponding to the number of particles in the interaction.
Just because P is one.
No, P is a collection of like momenta.
But in this theory,
Ah, okay, so let me further specify that because we are on a point, because the space-time is a point, there is no further kinematic data. There is no momentum.
There's no theorem. This is trivial.
Yeah, exactly.
The theorem is
In 0 dimensions, this would be, yeah, this wouldn't exist because there is no dependence on any kind of p.
I see. Okay.
Sorry, this was not clear, but good that you raised this issue. Okay, so
But I missed your point. So you said at some point that you cannot take the limit lambda to 0. This is what I didn't understand. This thing is definable on all of 0 and infinity, not including 0.
Yeah.
So what exactly can't you do by taking lambda to 0?
well, we cannot immediately say that it's a Pfaffian function on basically the full half-line because it's not analytic at 0. The Pfaffian function has to be analytic. So if we want to include this point in the description, we basically need a more general class of functions. That is what I'm trying to say.
But what would you like to say? That would you like to say that the graph of the function on the closed interval is still definable because it's just a closure. So of course it is still definable
Yeah.
in the defined.
If you're interested in just the definability, you could just add this by hand, take the closure. But we're interested more in also the complexity statements eventually. So yeah, we want to understand basically what kind of function is this on this full domain, and it's not Pfaffian. And in this case, you can just simply say, well, in this range, it's Pfaffian, and we add a point. But more generally, you will need a more, going beyond this example, you will need a more general function class.
Bit lost. So when you say it's Pfaffian on 0 infinity, you mean on any interval of the form A infinity where A is strictly positive? Because this K1/4, is it not oscillating very fast?
Not on the real line. No, it's,
It's not.
it's,
It's
yeah.
Modified one.
It's a modified.
it's a modified one. Yes, exactly. Yeah. This is not the one which has the oscillations. Yeah.
You're saying that it's not flat. I mean, you said that there were symptotic. I thought it would be flat, but maybe you corrected the flatness because you multiplied by e to the 1 over lambda.
Exactly. So somehow this factor e to the 1 over lambda takes out some kind of bad properties of this Bessel function. And
After this, you still have an asymptotic expansion. But, I mean,
Yeah.
you're claiming there is an asymptotic expansion, ak times lambda to the k. And it's not just identically 0 because you renormalize by this e to the 1 over lambda.
yeah, that the factor adds some special thing which just cancels out a certain mathematical behavior.
Seems to always be in physical theories that there's some factor, exponential factor taken out, so very similar to what you had.
Yeah, this is what you would expect from just theory of summation of linear ODE. You always have the exponential factor times some Gevrey.
Yeah, exactly. Of course, these are very simple theories, which are kind of toy models to kind of uncover some more general behaviors that I want to highlight. So another approach altogether is to indeed use this kind of summability techniques. Namely, we use the technique of Borel summation. So what we do is we perform the asymptotic expansion anyway, knowing that it diverges, but from the coefficients, we try to extract some information to say something about the function that it's supposed to be. Basically, by controlling the coefficients, you can make still some o-minimality statements. This is the next statement I want to mention. This again, together with Thomas, and this result is based on the master thesis of Giovanni Raffazzini, who is also here. So basically, if you take this polynomial P, be of even degree, so more generally than just pi to the 4, then all these amplitudes are actually Gevrey functions on an interval which now includes lambda to 0. So I'm not going to mention what these Gevrey functions are. It's basically a class of functions which has controlled summability properties. So perform this Bauer series expansion, and looking at the growth of the coefficients, you can still make some kind of statement about the asymptotic expansion. And in fact, these Gevrey functions have been shown to be o-minimal by Van den Vliet and Speisegger in the year 2000. Okay, so going beyond this, even in the non-perturbative case, albeit in a very simple toy model theory, we can still use these kind of more general o-minimal structures to say that the amplitudes are tame.
So when you say Gevrey, do you mean that it's just different, I don't know, different terminology in the literature? Do you mean that they are Gevrey on a large enough opening of a sector so that they would be quasi-analytic on the line 0, 1? So
Exactly.
it's one
Yeah,
Gevrey. Do
yeah.
you mean that they are Gevrey on a sector of opening more than pi?
Yes, so we depending on the power of this interaction, that determines the width of the opening. But we are basically only interested in restricting to this real interval. So we don't need any further.
Quasi-analytic on the real interval, you need to have the Gevrey bounds on more than a half space. Like you need to be Gevrey on more than the full half space.
Ah, yeah, yeah.
To be,
Exactly. This is satisfied in this
this
case.
is
Yeah,
in this case.
yeah, yeah. The main point here is that in these quantum field theory amplitudes, already in the simplest cases, we encounter these kind of more complicated multi-summable functions, which are also then tamed by this result. And I think later this workshop we will have a talk by Adele Paget, which will go more deeply into this kind of.
So your claim is in particular for 5 to the 4?
Yeah, exactly. So any even degree polynomial. Yeah.
Very surprising for me because I thought that they would not be Gevrey on this anti-Stokes lines where so you're doing on the real part, but there's no solution. I thought that this thing is multi-somewhere on every other line except for the grid line.
And somehow that is accomplished by this exponential factor.
Yeah, I thought even after pulling on.
Ah, okay.
But
Yeah.
Okay, I mean,
Yeah, we can discuss it a little bit later in more detail. Yeah. Okay, so of course these are simple examples in 0 dimensions, but ultimately it would be very interesting to go beyond this. And in the paper with Giovanni, we have a little bit of discussion on this, but this is where many more ideas will be required. So now, in the last part of my half of the lecture, before David takes over, I want to talk a little bit about complexity. Basically, we've now seen that some objects that naturally appear in quantum field theory are definable in an o-minimal structure. But the question is now, can we somehow refine this to sharply o-minimal structures, which were discussed this morning?
I ask a question.
Yes.
So this theory, so for each n, you get a differential equation satisfied by those guys. Is it
Yes.
understand the relation between the various differential equations that you get?
Yes. So yeah, well, we
hope that if for some n you have these properties, and you know that for all figure n automatically it will be.
Exactly. This is basically by integration by parts that you can always stepwise reduce it to sort of finite basis, and then this basis we construct a Pfaffian chain for. And by integration by parts, you can gradually expand the chain. So indeed, can we refine this to sharp o-minimality? And can we somehow quantify the tameness of all these objects? Okay. And in particular, this could give rise to a new notion of information in physical theories. Okay. Well, here there's a lot of open problems. I quickly want to give an overview of what is known and what is not yet known. So where can we already refine to sharp o-minimality? Essentially only in a handful of extremely special cases, because I mentioned here, we have this Pfaffian function. So here we can already directly see that it's definable in a sharply o-minimal structure, and we can quantify its complexity.
So I have one more question. So is there a single case where you do not start with an extra point, where you actually get this result in the non-perturbative case, and where you know that what you get, also depending on p, is really.
Yes, we have some results on that, but it's only for then extremely restricted physical processes. That's not sort of globally true for all amplitudes, but yeah, we have some observables which are even in a non-perturbative case. Yeah.
And can you say something why you need this even degree? So if I take phi 3, what do I get?
Then the integral doesn't converge to begin with. So it's basically this integral. So yeah, for odd degree, it doesn't. Yeah.
In the perturbation theory for the cubed case, was discussed by Mick in the Trent Simons paper, like all the Stokes wedges for that case. That's like
exactly
taking detail.
Yeah. So indeed, if you refine to some kind of supersymmetric theory, then you can also make these more non-perturbative space. Yeah.
You said that lambda is a real parameter?
Yes.
Do you ever think of it as being complex?
I guess in some theories you can have indeed complex parameters, and then situation will become more difficult. Indeed, I think this is what you will speak about, extending to the complex parameters. Yeah. In these cases, we focus on the real deformations. Yeah.
some sense you need some complex properties to be sure that you are actually definable on this line. Right? I mean, this general theory, it's very complex theory. It's not.
Yeah, exactly. So yeah, indeed, you go a little bit into the complex plane and ultimately restrict again to the real line. That's the range of parameters that you're interested in. Yes. But indeed, in the analysis, you go in the complex plane. Yeah.
So one more question. Do you ever think of n as another parameter for definability? I mean, you can ask, does this depend definably on n?
That's a great question. So essentially, the number of physical processes that we have seems to be depending also on discrete parameters, like how many particles do you scatter, for instance, these kind of things. These are integers. And well, in principle, it seems you can have observables for arbitrarily high n. And the dependence on those discrete parameters will then be very tricky to just make any Tameness statements of. So what you could, for instance, do is make complexity statements depending on n. So let's say you look at the complexity of this thing depending on n. And typically this complexity will end up going to infinity, but you can try to quantify how that complexity depends on the discrete label.
But I mean, here you have some specific integral. It was d phi, phi to the n or something.
Yeah,
like
yeah, exactly.
So I mean, okay, you could ask, does this converge, for other n's? I mean, is it, can I write an asymptotic expansion for that as a function of n?
You have in mind some kind of analytic continuation of n to real.
Like the gamma function, I don't know, you define it for integer
Sure,
n,
yeah,
but
yeah.
actually you can.
That could be an interesting
Sometimes
question.
it could
Yeah.
be defined for, so.
Yeah, that's very good.
I mean,
Yeah, I've never thought
I
of
don't
it.
know if you get, for different n, do you get different Bessels there, or is it very different? For example, if you took Bessel, but instead of one quarter, you took Bessel 1/4 plus n.
Yeah, yeah.
And then it's plausible, but it's also definable in this n, I think. You can do asymptotic with respect to the parameter, and there's also this multi-summable type expansion.
Yeah, we've never thought of that because we've always thought of n as a real discrete parameter. So basically the range of values that you take from quantum field theory would be just positive integers. But maybe if you indeed make it on the real line, you could make extended statements. Yeah, it's a great point.
But what we thought about is, and you make and baby statements about this, it's like it would be very nice to define sort of the complexity of observables, and then you immediately run into this problem, what you point out, that depending on this n, the complexity gets larger and larger. So you can write down explicitly the complexity depending on n. And so it just gets bigger and bigger, and it's kind of how do you associate the physical underlying theory, because then we said, oh, there should be some sort of complexity classes, like that. But indeed one could just measure the complexity as a function.
Yeah, exactly. Yeah, it's a great point. So let me quickly say what is not yet known. Well, if you want to think about complexity, the perturbative amplitudes, we've seen that we need periods to describe them. And this connects very nicely with the story we saw this morning, where ultimately this o-minimal structure R on X is basically too big to have a polynomially controlled notion of complexity. But if you specialize to a structure such as log-Noetherian functions, which still contain the periods, then you might be able to make complexity statements about perturbative amplitudes in generality. But this is something for the future. Even without having a very solid handle on complexity of amplitudes, we can kind of naturally speculate on what sort of things it depends.
Sorry, I just missed that. So you said it's not yet known to be in lnx, or it is known?
It is known that the perturbative amplitudes are in this structure, but it's not yet known if it's sharply o-minimal. So yeah, but this is very likely to be true. Yeah. Well, the general expectation for the complexity of amplitudes would be that it, of course, depends in a certain way on this initial data defining the quantum field theory, and in particular on this Lagrangian. So what you can think of is, well, can we quantify the complexity of this function and then see somehow through the calculations of quantum field theory how that translates to the complexity of the observables. So what kind of functions do you actually typically consider in quantum field theory? If you focus on what are called renormalizable quantum field theories, then the Lagrangian is always a polynomial. Okay, it's definable in R-Elge, and you can directly write down its format and degree, and kind of think how this format and degree propagates to the complexity of the amplitudes. But this is for renormalizable quantum field theories. If you think of a completely generic quantum field theory, typically you think of this as being so-called effective quantum field theory. And that's not the same notion of effective as we saw this morning. But this means that the Lagrangian is basically a completely general function, which is typically displayed as a general power series with infinitely many interactions, depending also on infinitely many real parameters. So if we want to make any finite complexity statements about these kind of functions, then something special needs to happen. And this is eventually where we return to this picture, where it seems to be, if we demand consistency with quantum gravity, then these kind of functions may still be described with finite information. And this is where David takes over, and I stop, and thank you.
Any questions, maybe?
Question.
Yeah.
So in these effective QFTs, these Lagrangian themselves satisfy some natural equations.
Exactly. So if we want to say that these guys are finite complexity, we will need ultimately to find some differential equation that's satisfied by these Lagrangians. We have hints that this is indeed the case. For instance, looking at renormalization group flows. Ultimately, this somehow sums to something that can be described with finite.
But you have infinitely many parameters there. I mean, it's a function of lambda n now for infinitely many lambda n.
Exactly. So to think of the tameness of this, that doesn't make any sense. So
in what sense can it satisfy a differential equation if you have infinitely many parameters?
So that would be the case if these lambdas themselves depend on a smaller but finite set of parameters, so that these lambdas themselves are actually describable by a finite dimensional space.
Thinking that this EFT arises from the RG flow of some completion with finitely many coupling.
Exactly, yeah. Then the idea is that through differential equations, there is some hope that it's finite information. Yes.
In your first theorem, you have the definability of this AKP related to some period. So it seems that from these inputs of the theory, you kind of have maybe a family of varieties of a variation of structure. Can you just comment? So which family should I think of? I mean, do you have like a family of Calabi-Yau or something? Then you take the period map into that family?
Right. So in calculating these perturbative amplitudes, this is done by these Feynman diagrams. I don't know if you've ever seen this, but this is basically a sum of finitely many diagrams. Each diagram you can then interpret it as a period over some Calabi-Yau. This is a very active research program where we try to basically geometrize these perturbative amplitudes. But it's a non-trivial step.
But then do you have the same picture here? I mean, is there some, should I think that there's some family of algebraic varieties behind the scenes, or it's just a special case of that first?
Yeah, so that dependence comes really on these kinematic variables P, which are absent in the zero dimension.
So this is going to be a very naive question. So I'm getting a little lost as to what we want this notion of complexity to do for us. As in, if you tell me some object is complex or not complex, what do I then know about it, or what can I calculate with it?
Right, so that is where these Tameness theorems come in, which I mentioned this morning, which may then have sort of quantitative analogs, where basically you say, well, what is the number of zeros of this function? What are the geometric features of these amplitudes or quantum field theories? This can then all be estimated to be some kind of finite number.
This may be, sorry, what?
This can then be estimated to be some precise finite described by this format and degree.
if the thing is not complex.
It's definable in a sharply o-minimal structure. And it has a complexity assigned to it, format and degree. And this then propagates to any kind of geometric question that you may ask about this object.
I mean, we investigate, for example, algebraic relations,
right,
for cosmological correlators. So if you have a measure of complexity and you know that your format is at a certain level, then you know that you don't need that every other that you don't need more building block function than this amount,
right,
to describe your amplitude.
Right. So
and everything else is related by an algebraic relation to the original set.
Right. So you need a finite number or some limited bounded number of sort of
Master
things,
integral
yeah, or Feynman diagrams or whatever else you want to calculate. So just to get clear on something. So the idea is that I give you the object whose I want to calculate. You calculate that its complexity is 3.5. And that tells me that I'm supposed to be able to write down 3 Feynman diagrams or something. Is that the idea? I'm sort of losing the drift as to what I'm going to do. So I'll give you an object that I want to calculate. What will you give me? And what do I learn from it? I'm trying to be very practical because I'm just a workaday physicist.
Yeah, so I mean, basically any kind of geometric question that you ask about these objects, like how many zeros does it have, how many times does it intersect a certain thing, anything that you can formulate in first order logic, which is essentially anything, anything that you then ask has a finite complexity. And this complexity depends polynomially on this degree parameter and this form of parameter.
But can you give an example of some property of these amplitudes that, okay, it's bounded because of this o-minimality stuff, and this bound has a physical meaning, right? That I can understand, say, like, what is the physical meaning of having only so many zeros on this amplitude, or so many zeros for the derivatives and so on? Give an example.
So it doesn't have to be zeros, it must be poles.
Anything.
Poles can maybe correspond to certain resonances in physical theory, a certain qualitative change in the physical process. And the amount of these you can then always estimate by form of the
I also have a small question. So in most of the examples, we took the Lagrangian to be a polynomial.
Yeah.
Could it also be a more general function than a polynomial, or is it atypical?
Exactly. So this is what these effective theorems.
Yeah.
We have a more general.
Yeah, but I also mean in the previous renormalizable case, then it's by definition a polynomial.
Yes, exactly.
Okay.
Yes, because basically you can have a very low degree. Yeah. Okay. If there are no more questions, then I the word to Ludovic. Thank you.
Okay, hello everyone. First of all, let me join Mick and thank the organizers for making this event possible and giving me the opportunity to speak here today. In this second part of the talk, we will make use of all the techniques and connections between Tameness and quantum field theory that Mick has developed to try to connect with the realm of quantum gravity. So let's get started. So one of the greatest challenges of theoretical physics in the last 50 years has been to unify general relativity with quantum field theory into a theory of quantum gravity. And doing this in the framework of quantum field theory alone, it's full of technical issues. You cannot simply add the metric as a new field, the space-time metric. So it soon became clear that we need to go beyond quantum field theory into some different framework, which for us the most promising candidate is string theory. Even today, after all these years, still having a full description of quantum gravity is an extremely challenging task, but fortunately for us, in many cases, we might not need to. So let's talk a little bit about scales. So as we increase the energy scale of a theory, quantum gravity effects start to become more prominent, and we reach a point usually called the Planck scale, in which the effects are already dominant. Quantum gravity becomes very dominant. And the thing is that this scale is 10 to the 15 times more higher than any experiment conducted on Earth. So in principle, for most cases, we can take a low energy approximation of string theory or of quantum gravity more in general, and construct what Mick was calling an effective field theory, that this could be understood as a quantum field theory, adding what we call a cutoff. This is a bound on the energy reachable by the theory that can be understood as a condition that rules out a sector of the possible configurations in field space that can be reached by the effective field theory. So if we go back to our original picture, our universe, this point here will be our description of quantum gravity, but at low energies, we have a plethora of effective field theory descriptions. The thing is that these 2 points, or these 2 regions, as indicated by the cone, are not decoupled. So the higher and lower energy regimes are intrinsically connected. And most of the effective field theories we can construct are actually not compatible with quantum gravity once we try to connect them to have a smooth connection from low to high energy regimes. So this is the idea behind the Sonland program. Which is the question, which effective field theories are compatible with quantum gravity? So to answer this question, the Sonland program tries to put conditions on the different quantities objects that Mick was describing on the space-time metric, on the space-time, on the field space, and on the Lagrangian. And these properties are usually phrased in terms of conjectures that try to establish in a more clear way the bound between these 2 regions. And the thing is that many of these conjectures are based in principles who have as a foundation the finiteness principles in physics. So let's discuss some of them to have a feeling of what we are dealing with. So the first conjecture I want to talk about is called the no global symmetries. The name is very self-explanatory. It says that in an effective field theory compatible with quantum gravity, we can have global symmetries. This is like, put it simply, a group acting on the field space that leaves the Lagrangian invariant. And the argument for this comes from black hole thermodynamics. And if we try to have an evaporation of a black hole in the process or in combination with the no global symmetries, then we violate entropy bounds. Which should be understood as a physical condition on the amount of information that a black hole system can describe. So in a way, demanding finiteness of information, it's already giving us a condition on the effective field theories that we can construct in this sector. Another conjecture that's very important in this discussion is the distance conjecture, which talks about the properties of the field space as a Riemannian manifold and its connection with the effective field theory as a whole. So if we have our field space, something like this is field space. And we take a geodesic along the space, going to infinite distance, then the effective field theory develops an infinite number of states that need to enter. And this signals again the breakdown of the theory.
Can I ask a question? So
yes.
This field space that you consider, it's finite dimensional, or you can even take it infinite dimensional?
In principle, we work with finite dimensionals, but yeah.
Some.
Yeah. But, yeah. So we take an infinite distance limit, and yeah, when we reach this, there is what becomes infinite. It's the number of states that are entering the theory, but it's like oscillation modes, for example, of a given field. This signals the breakdown of the theory, because well, it's many of the construction assumptions that we are taking to have the gravity entering as a simple correction no longer can be applied when this number starts to diverge. So as we see, this means that in effective field theory, we can only move finitely a finite distance in modular space. In the it will be later the modular space, and for now we call it field space. So from here we see that there is a strong connection, and there are many other results that point in this direction between finiteness arguments and quantum gravity. So we can say that the set of effective field theories compatible with quantum gravity are quite tame in comparison with all the possible quantum field theory constructions we can make. And so it makes a lot of sense to consider quantum gravity in the framework of o-minimality. This was the proposal that made by Thomas already 4 years ago, what we call the Tameness conjecture.
Can you repeat formally what is the distance conjecture?
Distance conjecture will tell us is if you take a geodesic path in the field space and go to infinite distance along this geodesic path, when you reach the infinite distance point, there is an infinite number of states and that have to be accounted in the description of effective field theory. And this causes the effective field theory to be ill-defined. So we have to, in order to have a effective field theory properly defined, we have to be sort of in a finite distance region around a given point. So going to the Tameness conjecture, it tells us that the effective field theories, the quantum field theories we should consider are precisely the ones Mick has been discussing in the first part of the talk. So it says that effective field theories compatible with quantum gravity are tame in the sense that in the field space and the Lagrangian are definable in an o-minimal structure. So let's see some consequences of this. In some motivation first, beyond the results coming from physics and finiteness, there has been a lot of mathematical progress in the recent years that makes this connection much more formal. So let's discuss some of the mathematical connections. And to understand these connections, the first thing we can ask ourselves is what kind of fields, what kind of field spaces enter in quantum gravity. And based in different examples, the simplest examples we can construct are theories with high degree of supersymmetry.
One more question. So
in
some sense, you are completely changing the question. So now we are really looking at the field space, and this is where definability is. It has no relation at all with the definability of amplitudes. In some sense.
For now, no. Now, once we start to discuss again about the Lagrangian, then we can have an interaction between both. But for now, most of the results we have coming from the Swampland program and quantum gravity are more related to the field space itself, more than the Lagrangian. So in configurations with high supersymmetry, this is known in generality, it's given by an arithmetic quotient. These are manifolds that can be written as a group of a semi-simple group, and you take the quotient by a compact subgroup of E, and then another quotient by a discrete subgroup. And the thing is that in 2018, Bakker, Klinger, and Zimmerman proved that all these kind of manifolds are definable in the simplest o-minimal structure with the semi-algebraic sets. Well, this is already interesting, but it's a sort of a simple example. Let's consider more physically interesting ones, which will be compactifications to 4 dimensions. So string theory is naturally defined in 10 dimensions, but to connect with the universe we usually observe, if we take a factorization of 10 dimensions in a 4-dimensional spacetime and a compact manifold, which can be taken to be a Calabi-Yau manifold. So what we actually do is we do not compactify over a single Calabi-Yau manifold at a time. We compactify over a family that's a family of manifolds that it's labeled by the choice of symplectic and complex structures. And this induces in the lower dimensional theory a moduli space that comes two sectors, a color sector and a complex structure sector. And these moduli spaces will be the field space in which we will focus on from now on, and more explicitly on the complex structure part, which is the one that is better understood for now in the context of tameness. But most of the results we discuss now, we expect that they will propagate to the color sector as well, but this is still a territory that hasn't been explored too much. So the thing about the complex structure is that all the physical quantities that will be described in the effective field theory in terms of the complex structure can be written in terms of the periods, with the period integrals, which are just the integrals of the holomorphic form over a basis of C cycles. And with this, using the periods, we can again represent all, for example, the metric of the moduli space, or the coupling, or basically the function centering in the Lagrangian. And as it has been discussed already several times, the period map is actually definable as well. In this case, in the bigger structure containing the restrictive analytical functions and the exponential. So again, it's a result by Badger, Klinger, and Zimmerman of the same year. So since the period map is definable, this means all these objects are definable as well. And so all the quantities we can construct with them also are definable in our effective field theory. Yes?
So are you using the fact that these integrals are definable, or are you using the fact that the period map into this quotient space is defined?
Basically, it's equivalent, I would say. Yeah.
They are both true, but it's much easier to show that the integrals are definable than to show that the map into quotient space.
Yeah, in principle, we are using this one. That's true.
Using just the integral.
Wait, that's how we end up expressing all the physical quantities, yes.
We're thinking about that to be in particular, or is it?
This is more general. Any kind of period integral that can be constructed from from the complex in the complex structure sector, it will apply. In general, this is a map that goes from the moduli space into a arithmetic quotient. So any kind of period associated to this kind of constructions will be definable in an o-minimal setting. Yeah.
But the actual physical quantities would be much more complicated than say the type 2A setting, because then you're talking about the hyperbole.
Yes.
So it's a classical complex structure. It's not correct.
Just try to understand where the quotient comes in. So if you're just using these numbers, these numbers are not living in a quotient, and they enter the Lagrangian, or the Lagrangian is somehow defined in terms of the quotient.
Well, many of the, for example, the metric of the moduli space, or the several coupling functions entering the Lagrangian can be written in terms of the coordinate that's given by the quotient of the period maps, like for example P2 over P1. In the case of we are working with a Calabi-Yau 6 threefold, but if we will compactify on a simple elliptic curve, we will have also these kind of behaviors that we have to construct the period map.
Quotient of the period map, or quotient
sorry, of the period integrals. Yes.
It's important that also sort of you are able to divide out the monodromy also in the physical quantities. So they really live in this quotient space, as you say. So it's not just in one individual integral, which appears there.
Yeah, I'm trying to understand if you use really the tameness into this quotient space, which is much
Yeah.
Yes. No, the periods are defined. Yeah. So sorry. Yes, they are defined into the quotiented part in which you have taken out the monodromy already. Yes. If not, then the properties, the functions that appear involving the periods will not be will not be tame. We need to restrict to the.
And this is what
Euler
actually
polynomial.
appears in the Lagrangian. So
Yes.
when you write the Lagrangian, it's the original integral, or is this integral where you assume that it lands in some
Yeah, this
normalized fundamental domain?
this tau lives on the quotiented moduli space. So we are taking like the lives in here. Yeah. Mhm.
It also fits with the idea that there are no global symmetries. So,
Mhm.
so if there would be a symmetry, then you have to divide it out. So yeah.
Yeah. And
One of these principles.
yeah, all the redundancies in the representation have to be always quotiented out. So you end up, you cancel all the symmetry copies and you end with a single one, which is where all the functions should be defined.
Or and you assume that the Lagrangian is subanalytic, for example, or definable? The Lagrangian is a definable function here?
That's what we expect. Yes, yeah.
Where you actually want to show that it is
Mhm.
like it comes out definable.
Mhm.
So you compute it using string theory, and then you show that it only depends on the periods.
Yes.
In a very well-defined way, and therefore it is definable. And that's kind of the evidence, one of the pieces of evidence that it's always definable.
Yeah, it's more based on observation and the construction of particular examples than. Okay, so well, one of the things we can see from here already is that we have to increase the size of the structure, and this is because the periods and the period map are very transcendental. But thanks to the fact that they are definable over a minimal setting, we have some control over the finiteness properties. So this is already like a nice improvement. And well, now that more or less the motivation for the definition of the conjecture is clear, we can try to see some applications of this o-minimal framework to quantum gravity. The first one I want to discuss is the finiteness of loss backward. Yes, backward. So we have this moduli space with these fields, but for phenomenological reasons, we don't want them to be completely free. We want them to be fixed at particular points in field space. And so to fix the moduli, one of the standard ones is to introduce an integral vector in the Hodge structure of the manifold that has finite intersection. This means that the integral over the manifold it's bounded. And this, when we introduce this into our compactification, this generates a function with a non-trivial profile over the moduli space. We call the superpotential, which is given by this integral. And the moduli space are fixed to extrema of this potential. So we have to do an extremization process. And this leads us to the flux backward, but in addition, it also induces a condition on the flux vector itself that we're imposing, that it has to be self-dual. This is what we call the self-dual locus, and it's a generalization of the Hodge locus that's going to appear in several talks later on. To recover the self-dual locus, we have to include, in addition to the extremization of the superpotential, the man need to be zero, and then we go back to the Hodge locus. So, well, the important result in this context is that we can ask how many ways can we have to fix the moduli, how many choices of P can we find for a given geometry, and there has been an important result by Baker, Green, Snell, and Zimmerman in 2021 that says that the set, the locus of self-dual classes G with finite intersection is definable in, again, R with the restricted analytical and the exponential. So this means that, for example, for the case of F-theory flux vacua, the number of self-dual vacua satisfying the tadpole constraint will have finitely many connected components. So from this, we can derive the finiteness of F-theory flux vacua. If we were to add to this formalism sharp o-minimality, then we could go beyond finiteness statements and try to actually have numerical bounds on the number of solutions, most likely depending on the tadpole bound, and maybe connect with what we call the tadpole conjecture. Another application I want to discuss is the very non-trivial relation between transcendental and algebraic functions over the integrals. In the context of the actionable conjecture. So we have seen that the periods are tame and transcendental. And we are now taking the equations that involve solving the period equations, so working with the periods over some integral classes. So as it was mentioned also in the talk by Bignamini, in this context, we have the Tila-Wilkie theorem. That tell us that the number of solutions for these tame transcendental functions over the integers are generally grow very slowly. They grow always subpolynomially with the size of the integers considered. So when we are looking for solutions on the number of solutions of a given theory in this context, if we take naive approximations or numerical computations, we will be most likely overshooting this value. That's not the end of the story, because in a recent paper by Van Vliet and Thomas from last year, they observed that when considering the Hodge locus of F-theory in several examples, there was a very intrinsic connection between symmetry and algebraicity. So when we go to symmetric points of the field space, of the modular space in this case, the transcendental part of the periods disappeared, and we arrived to an algebraic function again. So in this case, the Tila-Wilkie theorem couldn't apply because we wouldn't have the transcendental condition, and the number of solutions could be much higher than these bounds. And this connects as well with the results by Baldi, Klinger, and Ulmo from last year as well, relating to the level of the Hodge structure. So when in this result, they studied how the density of the Hodge locus changes with the level of the Hodge structure, and it turns out that when we go to symmetric locus on the modular space, the level of the structure goes down, and so we have more solutions. And one last application I wanted to discuss is the bounds on the volume growth of modular spaces. So we have been discussing a lot already about modular spaces and field spaces, but we haven't considered in generality the question what Riemannian manifolds can be modular spaces. Quantum gravity. So there has been recent work on this question by Matilda Delgado, Daniel Heistig, Raman, Torres, Bafa, and Xu, a lot of authors in this paper from last year. And it says that, well, the kind of modular spaces that we can find in quantum gravity have to satisfy the following volume growth conditions. So if we take a geodesic sphere around a given point in modular space, the volume it's bounded by the volume growth of a sphere in Euclidean space, where this is a geodesic sphere. It's a set of points in M, the modular space, that are at a distance at most rho with respect to a fixed point. So this result is very interesting because, well, I'm sure Matilda will discuss this in more detail in her talk later. But the thing is that this kind of volume growth bounds at, yeah.
Now I'm lost. So what are those moduli space you are talking about? What are they compared to the initial problem where you have the field, space of field and so on?
Well, in this case, our space of fields, we are restricting ourselves to the scalar sector of the field space, and these are the moduli themselves. Yeah. So coming from the Tameness geometry, these kind of bounds, polynomial bounds on the volume growth, are very natural. So if we have a time set in Euclidean space of dimension L, then the volume of A intersected with an Euclidean ball of radius R, it's bounded by a polynomial on the radius going to the dimension of the set of the dimension of L, where this coefficient basically measures the complexity of A, measures its related complexity of A, measures, for example, the number of wiggles, the number of times the set A is bent inside of the ball. So in principle, since the condition of A is tame is very important because this means that this number of bends is finite, and so this bound is well defined. If we remove the tameness, this can grow as any function. Well, this seems very reminiscent of the conjecture on the volume growth, but this is in a generic Riemannian manifold. And this is restricted to the case in which we are working in a Euclidean space. So what we, Thomas, Mick, and I conjecture to relate both explicitly this year is that in quantum gravity, modular spaces must admit a tame isometric embedding into Euclidean space. So if this conjecture were to be true, then the volume growth conjecture will be immediately satisfied. This is more restrictive than demanding pure tameness on the manifold. So for example, if we have the
what is the nature of metric?
Well, it's a Riemannian metric.
How is it?
Well, you can construct it by taking. You have there is a yeah, you usually have in the kind of constructions we're considering, you have a function that is a prepotential, and you take derivatives to construct like derivative of this form. They are Kähler spaces. So you are
spaces.
Yeah.
Give yourself potential for the kilometric.
Yes, exactly.
Yeah, they're kind of determined by physics. And there's like Will-Patterson tricks.
So yeah, the conjecture is actually about what sort of functions are allowed to arise as metrics on the space.
Yeah.
And in all the examples which one finds in these physical settings, this is actually true. And it's very non-trivial true, as we will see in the next talk. So it's because you're in fundamental domains and because you quotient out symmetries and so on.
Yeah.
So it's related to the other conjectures which were on the board before.
But sometimes those metrics are coming back from some period map.
Exactly. Yeah, correct. In these examples.
But you're saying in this example, is there some definition? So what does it mean that a metric? So what is the definition that says that you're saying the metrics that you can put on these spaces have to obey this? What does it mean that you can put a metric? I mean, you can put any metric I want on a manifold. So what is the restriction?
Yeah, so this is maybe the hardest part to get about this whole swampland story, and Kumran will give a talk tomorrow where he will voice this even better. It's kind of, you take all the examples, so you can imagine that string theory has been studied for 40 years, right? And the many examples have been generated in this process. So in other words, many examples of field spaces and metrics have been computed which come out of string theory in a well-defined procedure. And for all of these examples, these properties are true. And then you say, and then the bold move comes. This is recorded. So the very bold move is to say, oh, because it's true in all these examples, so I can abstractly formulate it and say it's always true in the theory of quantum gravity.
Wait, but there is some process where you start with string theory, then you produce
exactly
a metric on the modular space, and the claim is that this matrix
and then you check that
it
satisfies this.
Yeah, I understand it happened in examples, but just what is the conjecture? Conjecture is
And
whenever you generated the metric in this particular process, then that metric will satisfy this conjecture.
And then exactly. And then the conjecture is that this is a feature of quantum gravity and not just a feature of these examples. And the good conjectures, they often have more evidence. They then use kind of black hole physics, which is like even harder to understand in some sense. It's like a lot of arguments which we as physicists learned over many years to use in a clever way to argue that this should be true.
In some sense, is there a stronger, this conjecture would follow if you say something like the modular space has a natural definable structure, and for this definable structure, the metric that I construct on it is definable.
Yeah, this is not enough for this because, well, maybe we shouldn't stop you too much, but like for the hyperbolic at the upper half plane, everything is definable, but it doesn't satisfy this.
Yeah, that's what I was going to do.
Okay.
Yeah, well, the main idea behind these conjectures in most cases is funded by some general expectations, general physical arguments, and then supported by all the constructions that we have from string theory. But yeah, exactly. This is not a explicit mathematical condition. It's just an observation of the constructions that we have coming from string theory and quantum gravity more general.
Is there some additional kind of, I don't know, asymptotic flatness or?
And not necessarily, no. No, for example, in this case, the hyperbolic group has constant negative curvature. Yeah. So this, if we study the volume growth in this space, we have an exponential volume growth. So it doesn't respect this conjecture, and it does not admit time isometric embedding into clear space. To accommodate for this constant negative curvature, we have to bend the space infinitely many times, so it doesn't work. But for example, in type 2B, we never, or in other constructions in string theory, we never encounter these spaces alone. We have to quotient by the monodromies, and then we go to a space with finite volume, which does admit a time embedding into clear space. So in this way, we see that, well, this is the upper half plane with a hyperbolic metric. This is very tame as an object on its own, but still the time isometric embedding is a stronger condition. So a question for the mathematicians will be to whether it is possible to define a tame version of Nash embedding theorem, and knowing the conditions that the manifolds have to satisfy for them to admit this time embedding. Could bring some light on the kind of geometries that we can find in quantum gravity. And well, there are plenty more applications, but it's already like we're running a little bit late of time. So before I conclude, I would like to mention that, well, this has been focused only on o-minimality, but one can go further and try to demand sharp o-minimality. And well, in here, yeah.
Also that you mentioned there, like, do we mean the full moduli space of the actual quantum gravity theory, or is it like the moduli space of an EFT that's like a subset of the moduli space of the quantum gravity? Like, which one needs to have the SO?
We expect both.
Both.
Yeah. Yeah.
So the infinite difference ones are also.
Yes, that's exactly the main difficulty for the condition. Like, in principle, if we manage to have this under control, we expect this to tell us a lot of information about the nature of the infinite distance limits. So, well, I'm not going to get into the details, but with sharp o-minimality, we could upgrade all the finiteness statements into specific bounds, and we are working on a new conjecture, Mick, Thomas, and I, work in progress, that basically says that the effective field theories that appear in quantum gravity are not only tame, but also have finite complexity. And this is, well, we have two versions of this. One applied to the finiteness of, well, like any effective field theory in quantum gravity has finite complexity. Well, in terms of the format and the degree, which probably as a fact, depending on the cutoff of the theory we are working with. And then in relation with the question you were asking, the second one, it's more ambitious, is that the set of effective field theories is definable also in a sharp o-minimal structure. And well, with this I conclude. I hope that now it's more clear the way that tameness can be related to physical phenomena in general. We first started by reviewing how the connections appear in quantum field theories in more generality, and how they both fit in the context of perturbative and non-perturbative sectors. And then we went down and studied what happens in the context of quantum gravity, and so that o-minimality seems to connect very tightly with the different results coming from the Swanman program. And we can now go back to our original picture and answer the question of what's the language of physics with more confidence. And we can say that for quantum gravity, the o-minimality seems to be like a very good candidate. With this, I finish. Thank you.